let's say that I had an equation that looks something like this. Velocity equals distance over time. That's going to be one of the first equations that we learn in the next chapter. Okay? If I wanted to mathematically solve for distance, or that variable, mathematically, how do I go about doing that?
Multiply both sides by time.
Good. I'm going to multiply both sides by time, which means to solve for distance, I would take velocity times time. Okay? Yeah? Everyone feel good about that? That's good. Okay, what if I needed to solve for time?
Multiply both sides by time, then divide by velocity.
I can take both sides divided by time, and then I can divide both sides by velocity. Okay, the shortcut here is I'm going to just switch these two places. Okay, and I'd say that time is equal to distance over velocity. Okay, we're going to walk through how we can solve these equations as quickly and as efficiently as possible. So that little shortcut is going to save you a lot of time mathematically solving these equations. But you need to feel comfortable doing that. Okay, so does that seem too crazy for anybody? No?
Okay, so wait. You times both sides by the t?
Uh-huh. Yep, to get it out of the
I don't see
denominator.
the t on the other side though.
Oh, right here.
Okay.
Okay, and then I just divided by v on both sides.
Okay.
All right. Physics takes a lot of word problems. How many of you are freaked out by word problems? Don't be. Okay? We're going to get there. Don't need to be freaked out by word problems. I'm going to walk you through some basic steps that we're going to follow when we solve word problems. But word problems are almost all of our questions. Okay? But you're going to be able to do it. Okay? So first thing that we do when we have a word problem is to pick out and write down what we know. Okay? So you're going to start by writing down what we know. And when I say that, I don't mean write down the guy's name and write down what color car he's driving. Right? I don't care about that. Okay? If it tells us he's driving a yellow, like Toyota, 40 meters per second, what's the pertinent information out of that sentence? Yeah, the 40 meters per second, right? I don't care what color car he's driving. That doesn't make a difference to me. Okay? So we're going to write down what we know. My method and the way that I work is I like to make a list in the margins of my variables. Okay? So if I've got a piece of paper that has my questions on it, okay, blah, 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 there's my questions. I like to make myself a list in the margins over here where I've got space. So I know my time is equal to 5 seconds. My velocity is equal to 40 meters per second. I'm going to make myself a nice, neat list to keep my variables in check. Okay? It might seem simple when we've got 2 or 3 variables. Once we start working with problems that have 10, 11, 12 variables, you're going to have to give yourself a little bit more of an opportunity to be successful by staying organized. Okay, so just find a system that works for you. You don't have to make a list in the margins. That's just what you'll see me do on almost every single problem. Okay? Next, you're going to try to figure out what equation you should be using. Okay, so again, you're going to have an equation sheet that you accumulate as we go through these chapters. You're going to just keep adding to those equation sheets. Okay? So each chapter will kind of maybe get 3 or 4 new ones. If you've got your list of variables, you've got your list of what your word problem gives you, that's going to help you narrow down what equation you should be using. Does that make sense? Okay, so if I'm given velocity and I'm given distance, and I'm trying to solve for time, I'm going to look for an equation that has those 3 variables in it. Okay, and then I can start to plug in and solve. Okay, I think it's helpful for you to write down the equation first without numbers, just so you can see this is what I'm using. This is how I'm going to have to rearrange it if I need to do that. That's up to you if you choose to. Okay, we want to find out what we're solving for, what variable that is, and what unit should go with it. Okay, so let's look ahead to our overall goal. If my question is asking me, how far did this man travel? What might I be solving for there? How far did he go? Distance, good. And what would the unit most likely be? Meters. Yeah, meters or kilometers or miles or whatever our unit happens to be in that time. But we should be solving for distance. If we solve for time, we're not answering the question. Okay, so we've got to understand what we're solving for. And then you've got to look for the right units. Okay? So if I asked you, how long did it take for this to happen, what would I be solving for? Time. So these questions aren't going to say, solve for time, solve for distance, solve for whatever. It's going to ask you a real life question. And you have to determine what variable needs to be solved for based on that. Okay? Understood? All right. Then we plug in numbers and we rearrange and solve. Okay? You don't have to write down everything I have here word for word. Do whatever note-taking works best for you. Okay? Abbreviate things when you can. Condense things if you can. But once we've picked our equation, once we understand what we're solving for, then it's just plug and chug. Once we've got our answer, we've got to make sure that it makes sense. Okay? Look back at your answer. Were you expecting a really small answer, but you got something huge, or vice versa? Okay, so as you're working through these problems, you should be analyzing, I think I should be getting a relatively small number here, or you should be having an idea in your head about what your answer should look like. Sometimes that's really difficult to do, and that's okay, but just start thinking about what your answer should start to look like and see if it comes out like that. Okay? Do you have the right units? Yes or no? And then we've got to make sure that you're checking these things pretty extensively, especially on tests. Okay, because units are really, really important in physics. The reason that we use the metric system in the scientific world is that so when we apply things outside of the United States in the scientific world, other countries, people from other countries have an idea about what we're talking about. Okay, so we use it in the sciences because if we don't, if we give them measurements in pounds and ounces and degrees Fahrenheit, things like that, it's confusing, right? We've got to give it to them in the way that everyone else uses it, not just us. Okay, so we know giving a consistent measurement there. Okay, SI units are converted to different measurement systems in most countries. Realistically, not most countries. Most countries use the metric system, so I'm not sure why I included most there. But we can convert the metric system to the U.S. system with a couple different conversions, and I'll give you those here in a little bit. Okay. Here's the base units that I need you to know for different types of measurements. You don't need these bottom three, just the top ones. Length, mass, time, and temperature. You need to know those base units. What are they normally measured in? Okay? Does anyone have a guess as to why the base unit for mass is kilogram instead of gram? Yeah, Andy, what do you think?
It'll be a smaller number if I
Yeah, exactly. A gram is a really small unit. And most things that we measure, we would be dealing with thousands and thousands of grams. Okay, so using a kilogram as the base unit gives us a little bit more manageable numbers. Okay, we're not having to deal with hundreds of thousands of grams or thousands or whatever. We're going to deal with a little bit more manageable numbers of kilograms. Paul, would you agree that's the reason?
Yeah.
Cool. All right, now here's all of our prefixes. Metric system conversions are on a scale of 10. Okay, so here's the prefixes that I would like for you to know. From mega, and then one past the red down here into nano. Mega to nano. Yeah, I'm going to explain the right portion of this. I'm going to talk about these over here in just a second. So if you don't want to write this portion down just yet, you don't have to. I'm going to explain a little different way to write that here in just a second. The other ones you will need to know the abbreviation that goes with the prefix. For micro there, that's what that looks like. Okay, it looks like a little U with a tail on the front. All right, so this is kind of what our chart is telling us, and this is how I'm going to show you how I apply it. Okay, because I write it just a tiny bit differently than they do. What this is telling us is that 1 centa of the base, so let's just deal in meters here, because that's the example that they give. 1 centimeter is 10 to the negative second of a meter. Okay, I don't like dealing with negative exponents. I don't really like dealing with decimal places all that much. Okay, so I'm going to kind of flip that around so that the bigger unit gets the 1. Okay, so between a centimeter and a meter, which of those is the bigger unit? A meter, right? Between centa and the base, a meter is bigger. Okay, so let's start here with deci. This is where the base fits in right here. Okay, a kilometer is bigger than a meter, but a decimeter is smaller than a meter. So that's where the base fits in, right in between those. So this right here is telling us that a kilometer is equal to 1 times 10 to the third meters, or 1,000 meters. So that's where the bigger unit still gets the 1. I'm going to start at decimeter, kind of describing this how I use it. Okay, so for deci, I want the bigger unit to get the 1. So is meter or decimeter bigger? Meter. So I'm going to say 1 meter is equal to how many decimeters? 10 decimeters, right? Because here our chart tells us that a decimeter is 1/10 of a meter. All I'm doing is flipping that around so that our bigger unit gets the 1. Okay? So for centa, I know 1 meter is equal to how many centimeters?
100.
100. Okay, because here it says that a centimeter is 1/100th of a meter. Okay, so if I move down to milli, 1 meter is equal to how many millimeters? 1,000. 1,000 millimeters. Yeah? And then if I move to micro, a meter is equal to 1 times 10 to the 6th micrometers. And then for nanometers, it's times 10 to the 9th. Okay? So the only thing I did between these was flip them around so that the bigger unit always gets the 1. Okay? If that confuses you more, then don't worry about it. Just go with what the chart says. Okay? But that's kind of how I'll work through my conversions. Is I like to give the bigger unit the 1, and I like to tell how many of the smaller unit is within that. Does that make sense? Or not so much? Give me like a yes or a no. Okay. Okay, make sure that you ask if you have questions, because these conversions and these prefixes are going to be something that we use a lot. Okay, so I need to make sure that you're comfortable with that. So when I do unit conversions, the first thing I do is write what I know. 193 inches, and I make my T. Okay, if I want to go from inches to miles, what's the logical pattern? What's my stepping stools basically to get there? Inches to feet to miles. Yeah. Do we need to go to like yards or anything? No. No. Okay. So, in my T-chart, I write what I know, and whatever I want to get rid of, it needs to go opposite of that, diagonal from that. Okay? So, inches would go on the bottom, and we said we want to go from inches to what? Feet. Good. So feet's going to go right on top of that. Then I'm going to draw that next section of my T-chart. Okay. Then if I want to get rid of feet, it's going to go diagonal from that. And I want to go from feet to miles. And then that is going to be where I stop, right? Because I'm going to cancel my inches, cancel feet, and I'm going to end up in miles. So now I have to plug in the numbers that go with it. So our conversion between inches and feet is what? Which one of those is the bigger unit? Feet, right? How many inches are in 1 foot?
12.
12. And then mile is bigger, so how many feet are in a mile?
5,280.
Good, 5,280 feet. If you don't have that conversion memorized, you might want to put that one in your notes. 1 mile equals 5,280 feet. What I want? Okay, I want to be in miles. So in my T chart, I multiply across the whole top, hit enter, and I divide by the whole bottom. Okay? So if in your calculator, you have to be careful. You either need to divide by parentheses, 12 times 5,280, or you're going to take 193 divided by 12 divided by 5,280. Okay, you got to be careful about how you plug it into your calculator there. Should we be getting a big number or a small number?
Small.
We should be getting a really small number. All right, Manny, tell me what you got.
0.003060859.
That's good. Thank you. 0.003 miles. Do we agree?
Yep.
Okay, if you're not getting that to come out into your calculator, I need you to tell me so I can come help you. Okay, anybody not getting that to come out? It's okay. I just need to know. Okay, be careful when you divide. It's either 193 divided by 12 divided by 5,280 in your calculator, or divide by parentheses 12 times 5,280. You've got to be careful there. Okay? All right, we did a US conversion. Now let's do a metric system conversion. Okay, so in my T chart, I'm going to write down what we know. To go from millimeters to meters, do I need to go to centa and deci and then meters? No, I don't. I'm going to go right from millimeters to meters. Okay, and I put millimeters on the bottom here because it needs to go diagonal from millimeters because I want them to cancel. So if I want to cancel something, it's got to go diagonal. Okay? So which of those is the bigger unit? Meters. And how many millimeters are in a meter? 1,000. Good. Okay, these prefixes you're going to use a lot that you're going to become really familiar with, but until that point, just keep referring back to that chart. Okay? So all I need to do is divide by 1,000, or realistically, all I needed to do was move the decimal point 3 places to the left. That's all I realistically had to do. Divide by 1,000, or I could just move that decimal place 3 to the left. So which one of these conversion system is easier? The metric system, especially if you're not from the United States, right? Okay. A lot simpler because everything's on a scale of 10. Okay, I might give you a velocity in kilometers per hour, but the distance you've been given is in centimeters or in meters. Right? We have to have things that match in our physics equations. So if I give you velocity in kilometers per hour, but I give you a distance in meters, kilometers and meters don't match. So you've got to be able to convert quickly. You've got to be able to pick out that you need to convert. Okay, that my units don't match here. I need to make them match. So consistent units here throughout your problems are really important. Because if you've got multiple equations and multiple variables and you end up solving your whole problem out using the wrong unit, your answer is going to be off by powers of 10, right? By 3 or 4 decimal places if you don't have that unit right. Okay, so just be aware when you start these problems that you're really going to have to pay attention to units. Maybe not like you have in the past. Okay? Because if you don't have those consistent units, you can be off by pretty major values. All right, here's some US to metric system conversions. You'll have to have these ones in your notes too. And then we're gonna try some more conversion practice. kilometers. How many centimeters did he run? I don't know where I lost my Y at. How many centimeters did he run? And then also, how many miles did he run? All right, let's convert to centimeters first. Start with what you know. If we're going to centimeters, should we be expecting a big number or a small number? A big number. Good. Good. Okay, so kilometers. We want to go from kilometers to what? Centimeters. Do you have to go to anything in between those two? I would. I would go to meters in between. Okay? The base is always going to be kind of our middleman. So I would go kilometers to meters, and then meters to centimeters. Okay? You could theoretically go right from kilometers to centimeters if you know that conversion. But until you feel really, really comfortable, it's probably best to stop at the base. Okay? So in 1 kilometer, there's how many meters? 1,000. And in 1 meter, there's how many centimeters?
For the centimeters,
Mm-hmm.
I think I had 243,300.
Perfect. Okay, do we agree? We're going to multiply by 1,000 and multiply by 100. Another way you could go about that is moving the decimal place. So I can move the decimal place 3 for 1,000, then 2 more for 100. I get the same thing. Okay, I can move that decimal place. Now I want to convert to miles. Could I convert from kilometers to miles? Yeah, I could do that. I could also convert from centimeters to miles. It doesn't matter. It's the same value. This value and this value are the same. It's just a different unit. Okay? It's representing the same number, the same length. It's just a different unit. So you can start with whatever you want. Okay? Go ahead.
No.
Go to miles. So I'm going to start from centimeters. Okay, and if I want to go from centimeters to miles, what might I do? Go from centimeters to... Okay, you can go centimeters to meters. Then meters to what? Feet, good. And feet to miles. Yep, feet to miles. You could also go centimeters to inches, inches to feet, feet to miles. Okay, there's a couple different ways that you can go about solving for this. It might throw your answers off a little bit just because of the rounding and the conversion factor between the U.S. system and the metric system. Okay, so that's okay. Matt, what'd you have?
I got 18.142 miles.
Let me see. 2 inches, you would have been an inch right there, and you went from inches to miles. You're saying there's 5,280 inches in 1 mile. You're missing the feet. Okay, did you write it all the way out? Okay. Perfect. Good job. Yep. As long as you're okay with the conversion part of it. Okay, did we get about 1.5 miles? We're gonna order off. What's this? It would be 30. Yes. Yeah. So did you get about 1.5 miles? Okay, so listen up. We should have got about 1.5 miles. Okay? How many of you have run a 5K? Okay?
I haven't run it, but I've kind of run half of it.
Run half of it. Okay, so you ran about this distance, right? A 5K is 5,000 kilometers. So if he ran 24 or 2.4 kilometers, right? A 5K is 5 kilometers. He ran 2.4 kilometers. That's about half. Okay, a 5K, do we know, is about how many miles? About 3 miles. And we end up running about 1.5 miles. Okay, so if you can think that critically through that, you'll know to check your answers to be about 1.5. Okay? So just think about big picture-wise. The first time I plugged this into my calculator, I forgot a step. And I came out with a really small number, like times 10 to the negative 4th miles. So knowing what I know about kilometers, I had to tell myself that can't be right. So then I go back, check my math, fix my problem. Okay? So to be able to think critically through that to check yourself. Okay? All right, let's try this one. How many seconds are in a leap year? What's our starting number here? Yeah, 366 days. Okay, so even though it doesn't look like we have a starting amount, we really do. Okay, so 366 days. We're going to go days to hours. Good. Then hours to... Yeah, we can go hours to minutes to seconds, or you can just go hours to seconds. That's fine. I'll go ahead and include every step, but most people know that in an hour there's 3,600 seconds. Be careful when you're filling in this hours and minutes and seconds part, because I've seen way too many people say 60 hours is equal to 1 minute. Okay, when it's not. Okay, so just be careful when you're plugging those numbers back in. Are we looking for a big number here or a small number?
Big number.
Really big number. Last type of conversion I want you to look at is this velocity conversion. So we're going to go from meters per second to miles per hour. And it works just a little bit differently. Okay, so we've got a bird that's flying 1.3 meters per second. What's per mean? What does that word mean?
Every second.
Every second, but mathematically per usually means what?
For every second.
Yeah, but it means divide when we're talking about math, right? If I say per, that means over, okay? So I'm at 1.3 meters every 1 second. Okay, so it's got to be divided by meters per second. So in this one T-chart, I need to do 2 different conversions. I need to convert from meters to miles, and I need to convert from seconds to hours. So I'm going to do it in one T-chart, okay? So let's go meters to miles first. Meters to feet. Feet to miles. And again, there's a couple different ways you could go about that. But 0.305 meters. Okay, so if I would stop right there, my meters have canceled, feet have canceled, I'm left with miles per second. Is that what I want? No, I don't want miles per second, I want miles per hour. So I need to keep going. And if I want to get rid of seconds this time, where do I need to put it? On the top. Good, very good. Needs to go diagonal. So I'll go seconds to minutes. You could go straight from seconds to hours if you want, but I'm going to show the whole thing. So 60 seconds in 1 minute, 60 minutes in 1 hour. Now my second unit has canceled and my minutes units have canceled, which leaves me in miles per hour. Okay, that's what I want, miles over hours. So now I multiply across the whole top, then divide by the whole bottom. This one's a little bit more difficult to envision if we should be getting a big number or a small number, but you should be able to think critically about how fast that really is and think about it in terms of miles per hour. All right, Noah, what'd you have?
I'll have an answer.
Okay. Figures, everyone's favorite. Just for the first day. What do most of the rules for significant figures have to deal with? What digit? Zeros. Good. Most of the rules for significant figures have to deal with zeros. So that's what we're going to look at. How zeros can kind of mess with our measurements just a little bit. Okay? All non-zero digits are significant, are considered significant. So any digit that's not a zero is always considered significant. This might be like the third time you've seen these significant figure rules, okay, but too bad. Okay, non-zero digits are significant. Zeros to the right of digits after the decimal point are significant. So what that's telling us is that if I have a number that looks like this, 8.000, how many sig figs do I have? 4 significant figures. I have 4 significant figures. 1, 2, 3, 4. Okay? This is telling us that I'm measuring it to exactly 8.000. Okay? That's telling us it's exactly 8.0. It's not in the 8 range. It's exactly 8.00. Okay? So zeros to the right of digits after the decimal point are always significant. Right of digits after decimal point are significant. Okay? Zeros to the left of digits, whether they're after or before the decimal point doesn't matter. Zeros to the left before any digits start are non-significant. Okay, non-significant. So I'll make this a little bit bigger here. 0.0860. How many sig figs do I have? 3. I have 3. My 3 sig figs are 1, 2, 3. This 0 is to the right of digits after a decimal point. These zeros are to the left of digits. Okay, whether it's before or after the decimal doesn't matter. They are to the left of digits. So anything before digits start are non-significant. They're just placeholders. Okay? Questions? All digits used in scientific notation are considered significant. Okay, and that's not in the expanded scientific notation. It's just what we see. Okay, so if I have 4.28 times 10 to the 4th, how many sig figs? 3. I don't care about the expanded version. Okay, zeros between digits are significant. So this one is significant because it's between 0. This one is to the right of digits after a decimal point. Plus, it's in scientific notation. So it's significant. Some numbers, we don't know how many significant figures there are. Okay, and they are considered what we call ambiguous. Ambiguous means we don't know how many significant figures we have. Okay, and ambiguous numbers are numbers that have what I call trailing zeros with no decimal point. So for example, this number, 120,000, we don't know how accurate that measurement is. Okay, these are what I would consider trailing zeros, right? No decimal point there, that's a comma, and no decimal point. So we're not sure if this is in the 120,000 range or if it's exactly 120,000.0000. Okay, we don't know. So there's a couple ways you can fix ambiguous numbers. And this is something that you need to know right here. Okay, we can fix ambiguous numbers by using scientific notation, by putting that number into scientific notation, or we can fix it by adding a decimal point. So if I know that number is exactly 120,000, what would be the better fix? Scientific notation or adding the decimal point?
Decimal?
Decimal point. Okay? Because if I know it's exactly 120,000, I'm going to add my decimal point. So 120,000, there's my decimal point. Can I leave it like that? No. It's not the end of a sentence. Okay? You've got to add at least a 0 there. Okay? So if you add a decimal point, it's got to add a 0 with it to tell us it's exactly 120,000. Several people try to just add the decimal point and then just stop. Okay, you have to have a 0 that goes with it. It's not the end of a sentence. Okay, so how many sig figs do I have with this number?
6.
7. 1, 2, 3, 4, 5, 6, 7. 7 sig figs. If I think it's just in the 120,000 range, boys, if I think it's in the 120,000 range, what would be the better fix? Using scientific notation or using the decimal point? If it's in the range, let's say it's 119,950. I'd want to use scientific notation, so I might say 1.2 times 10 to the what? Fifth. 1, 2, 3, 4, 5. Okay, why is, let's just think about it like this, okay? 1.2 times 10 to the positive fifth or negative fifth? I know you know now, but it's the positive fifth, and why is it to the positive fifth? Yeah, I moved the decimal place left, but also the number I'm trying to express, 120,000, is greater than 10. So if that number is greater than 10, the number I'm trying to express, if it's greater than 10, my exponent on scientific notation is going to be positive. If the number I'm trying to express is less than 1, my scientific notation exponent is going to be negative. A lot of people get mixed up with that, so just be careful. All right. We are going